On this worksheet, we're going to go through a few different types of Claisen condensation reactions. The first couple problems we're going to do is going to involve drawing the mechanism for a Claisen condensation reaction. So the first thing that I'm going to do here is draw on the alpha hydrogen atoms for this molecule. To find them, we're looking for the carbonyl carbon. Next to that is the alpha carbon, and then here's our alpha hydrogens. The base that we're using in this reaction, which is methoxide OCH3, it is going to abstract that alpha hydrogen and create an enolate, put the lone pair of electrons from the carbon-hydrogen bond onto that alpha carbon atom. Gives us this enolate right here. That enolate is going to react with a second version of the exact same aldehyde, or excuse me, the exact same ester. The enolate is going to attack the carbonyl carbon, and that will open up the carbon-oxygen double bond. It's going to connect those two molecules together. So this, what I've drawn here is the ester after it has been attacked, and now I'm going to create this bond to the carbon atom of the five-membered ring, and then attached to that, I'm going to have, attached to the exact same carbon, we're going to have a carbonyl group and our ester group, like that. Kind of ugly to look at, but that's okay. The next thing that happens is that we will close that carbon-oxygen double bond, and to do that, we're going to need to get rid of that OCH3, the OR group of the ester. So that is going to give us this molecule right here. Looks like this. So we've lost this group right here. I think maybe I'm going to number these carbons. There's carbon number 1, there's carbon number 2, there's carbon number 3. And this is the product for the reaction. This is where these reactions stop. So they're pretty similar to an aldol reaction in terms of the mechanism, but they don't undergo any sort of dehydration or condensation reaction afterwards. Let's do another example. So down here, we're looking at our next one. First thing we want to do, first thing we always want to think about are the alpha hydrogens. We're going to draw those alpha hydrogens in, and then we're going to use our base to abstract one of those alpha hydrogens to form an enolate. That enolate is going to attack a second identical ester. And the attack is going to be at the carbonyl carbon, open up the carbon-oxygen double bond. First, I'm going to draw the ester that was attacked right there. And then here is the ester that did the attacking right there. And I'll go ahead and number these carbons. 1, 2, 3, 4. This is number 1, this is number 2, this is number 3, and this is number 4. The carbon-oxygen bond closes up and gets rid of the OR group, whatever the OR group might be. And that's going to give us this molecule right here, a ketone slash ester, carbon 3, carbon 4, carbon 1, carbon 2. And again, this is where the reaction stops. Next, we are going to retrosynthesize. So we're going to be thinking about what two esters could we combine to give this particular molecule. So when we're doing this, and again, we're not asked to draw a mechanism here, just predict the esters that we need to combine to get this product. When we're looking at this particular product, we're going to be able to find the whole entire structure of one of the esters in this molecule. So we've got, that's my first goal, is to find that one completely intact ester. So the first thing I want to do is find the carbon-oxygen double bond that is adjacent to the carbon-oxygen single bond. That's going to be part of the ester. And then from there, I want to continue on from the oxygen, the single bonded oxygen, I want to continue on to the R group. And then from my carbonyl side, I want to continue, but I want to, when I get to this part right here, I want to move not towards the next carbonyl group, but in some other direction. So in this case, we're going to go this way. I don't want to move towards the next carbonyl group because each ester that I started with only had one of the carbonyl groups. So one of these belonged to one of the esters and the other belonged to the other. So what I've highlighted here is a complete and intact ester. This was one of the esters used for this reaction. The other portion of the molecule, so this much of it right here, that was the other ester. It's not the whole entire thing, it's just lost its OR group. So we just need to add an OR group to this second ester, and usually both esters have the same OR group. But honestly, it doesn't really matter what it is out here. You know, you could kind of say whatever you want out here because whatever it is going to get removed. Let's practice that same process with this one down here. So first, our first goal is to find the one whole entire intact ester. That's going to involve the carbon-oxygen double bond next to the carbon-oxygen single bond. And from the single bonded oxygen, continue out to your R group right there. Go back to the carbonyl group and work in the other direction. So we're going to continue down the carbon chain. From this point, don't go towards that next carbonyl group because that belongs to ester number 2. Just pick everything else. So this is one of the esters right here. And our other ester is this portion of the molecule. The only thing that's missing from its structure, again, is the OR group, and typically we're just going to match the two OR groups to each other. Next, we're going to draw the mechanism and predict the product of a crossed Claisen reaction. So this is one between two different esters. First thing that I'm going to do is take a look at where my alpha hydrogens are. Fortunately for this particular reaction, this molecule right here, here's its alpha carbon. It has no alpha hydrogens on it at all. It has 1, 2, 3, 4 bonds. None of those are bonds to hydrogen. So this ester is the only one that has alpha hydrogens. And because of that, this ester is the only one that can become an enolate. So this is going to make this reaction a little bit easier. We're not going to have as many possible products. First thing that we want to do is deprotonate and form that enolate right here. And then we're going to use the enolate to attack an ester. I am going to attack the other ester. We'll do that first. It's going to attack at the carbonyl carbon, open up the carbon-oxygen double bond, and that will give us opened up that carbon-oxygen double bond. That gives us this. Plus, I have formed a bond to this carbon right here. That carbon is bonded to a benzene ring. It's also bonded to a carbonyl group and a OCH3 group. That is going to, the lone pair on the oxygen atom is going to come back down and reform that carbonyl group, and that will kick off the OR group. So that will give us this product right here. It is also possible for this enolate to attack another identical ester. So let's draw that reaction as well. I'm going to just go straight to the enolate, this guy right here. I'm going to redraw that enolate, and then we're going to draw a second identical ester. It can attack that. At the carbonyl carbon, open up the carbon-oxygen double bond. We're going to begin by drawing that ester that was attacked. There's an O negative right there. Plus, we made this new bond. I'm going to stick it out over here to the side to this carbon atom right here. That carbon atom has a benzene ring, and it also has an OCH3. Then let's close that double bond back up and get rid of the OCH3. And that's going to give us, I'm going to draw it all the way over here, a benzene ring followed by a CH2, carbonyl carbon, another CH2. I lost a piece of my molecule. Back up, back up, back up. I lost a piece of my molecule when I put the two together. This is the risk that you take when you don't number your carbons. Okay, so I started back over, drew this right here after it's been attacked. Now I need to draw this carbon atom. I'm going to put some numbers on these carbons. 1, 2, 3, 4. So here's 3, here's 4, here's 1. Carbon number 1 is bonded to the benzene ring and also bonded to carbon number 2, which is part of a carbonyl group. Now I'm going to close that double bond back up. We're trying all of this again. Get rid of the OCH3. There's carbon number 3. There's carbon number 4, which is part of the double bond oxygen. There's carbon number 1. Carbon number 1 has a carbonyl group attached to it, which also has an OCH3 attached, and carbon number 1 also has a benzene ring. And then last but not least, we're going to make a prediction about what two esters would we combine to get this particular molecule. Again, we want to begin by finding the one ester that's intact. So the carbon-oxygen double bond next to the carbon-oxygen single bond. Work your way to the right and also work your way to the left, but stay away from carbonyl group number 2. Here's one of those esters right there. And our other ester, the part that's not highlighted, it's just missing its OR group. In this case, we're going to give it an OET group. We've got one more of these to practice. Find your intact ester group, work your way to the right, work your way to the left, avoiding that other carbonyl group. And let's draw. First, we're drawing the highlighted portion right there, and then draw the other portion of the molecule. It's missing its OR group. Match the OR group up from the other molecule. The last thing that we're going to do on this worksheet is called a Dieckmann reaction, and this is just an internal or intramolecular Claisen condensation reaction. So here we have a diester, and for this, we're just going to be attacking one ester group from the other. So I'm going to begin by identifying the alpha hydrogens. We have some over here. We also have alpha hydrogens over here. We'll use the ethoxide to deprotonate. It doesn't matter which alpha hydrogen we grab originally. I'm going to grab this one, and then I'm going to draw the structure of that enolate that I get. Negative charge right there. That enolate is going to attack the other carbonyl carbons. It's not going to attack the carbonyl carbon that's right next to it. It's going to attack the other one and open up that carbon-oxygen double bond. In doing so, we're going to create a bond between, I'm going to number these carbons, we're going to create a bond between carbon number 1 and carbon number 5, which is going to turn this into a cyclic molecule. And the cyclic portion is going to be between 1, 2, 3, 4, and 5. So that means that this is going to become a 5-membered ring. Now I'm going to begin by drawing the 5-membered ring. 1, 2, 3, 4, 5. Carbon number 1 is now the oxygen with the negative charge, and it also has that OET attached, this OET out here. Then we have 2, 3, 4, 5. 5 to 1 is the new bond we created, and coming off of carbon number 5, we also have carbon number 6. Carbon number 6 is a carbonyl carbon with an OET group. We are going to put that carbon oxygen double bond back and get rid of its OET, and that will be the end of this reaction. Because this is a symmetrical ester, cyclic type thing, we're not going to get a different type of product. So if we did this reaction instead by removing one of these alpha hydrogens and attacking this way, we would end up with the exact same product.